All right, so yesterday we talked about ways to create alcohols by reducing ketones or aldehydes. We said if you reduce a ketone, you can make a secondary alcohol, and if you reduce an aldehyde, you can make a primary alcohol. And we said the reducing agent we normally use for these reactions is sodium borohydride and some sort of alcohol solvent. And we showed the mechanism yesterday before we left, where hydride will attack that carbon, kick up electrons onto the oxygen, and then you have a proton transfer. So in this case, we had a ketone, so we're getting a secondary alcohol. But let's continue on. We need different reducing agents if we're going to be working with anything beyond a aldehyde or a ketone. So let's discuss reducing agents for carboxylic acids or esters. And I'll show you guys why we need a different reducing agent. And that's because we've got a problem. Let's say we've got this ester and we throw sodium borohydride at it and some sort of alcohol solvent. We get no reaction. Sodium borohydride doesn't have enough oomph to actually drive this reaction in the forward direction. So we've got to change the reagent that we use. And in this case, we're still going to use a hydride reagent. But what we use is lithium aluminum hydride, so LiAlH4. And then in step 2, we treat this with water. Essentially with esters, what this will do is split it into two different products. So this side will come off as one chunk, and this side will come off as the other chunk. So let's split this apart. That green chunk will be converted into an alcohol. And then the blue chunk will also be turned into an alcohol as well. Whoop. So can you guys see how we've kind of deconstructed our ester into two different pieces? This only works with lithium aluminum hydride. It won't work well with sodium borohydride. One thing too I wanted to note is that this reagent, lithium aluminum hydride, LiAlH4, is the same thing as LAH. So you may see it written both ways in your textbook or on sapling. LAH is lithium aluminum hydride. It's not anything different. So let's take a look at the mechanism for this. All right, so I'm going to kind of condense this a little bit. And I'm going to draw in the methyl groups just so we can keep track of everything. So just like before, we've got this hydride source over here, and aluminum's got the negative charge, and lithium's our countercation. And we've got a really strong dipole where this oxygen's pulling a bunch of electron density away from that carbon. So just like before, this hydride was going to attack in, kick up electrons onto the oxygen. We've delivered a hydrogen there. However, now this oxygen's got a negative charge. Do you think we're going to protonate it?
Yeah.
We could, but that's not getting us towards our product splitting apart. So what I want you guys to do is to try to figure out a plausible mechanism through which you can split this molecule into two different fragments, and then see if you agree and talk with your neighbor about it. So the question was, what's the mechanism through which we can get 2 moles out of this? If you feel pretty confident, give me a thumbs up so I can see some thumbs down. All right, I'll give you guys a little bit of a hint. We previously saw reactions where we were kicking off a leaving group, right? I'll show you guys a good leaving group here. This can act as a leaving group. Oh, now what? That's a hint. How are we going to kick off that leaving group? Is it going to fall off on its own, or do you think it's going to be shoved off? Shoved off. All right, so let's try to make sense of this. We're going to kick these electrons down and just eject off this leaving group. It's not the world's greatest leaving group, but it's good enough. So in this case, let's take a look at our two products that we get out. We formed an aldehyde, and then we've formed an alkoxide over here. That seems reasonable in my opinion. All right, so now the question is, how are we forming two alcohols? I said up here, we're forming that green alcohol chunk and that blue alcohol chunk. So what do you think could happen with that aldehyde? Water could attack, but let's also assume we've got extra lithium aluminum hydride around too. Yeah, we could do it again, right? In the first reaction, we had a hydride attack a carbonyl. We've recreated a carbonyl. So if we've got extra lithium aluminum hydride, we could attack it again. So let's go ahead and do that. So I've got my lithium aluminum hydride floating around. We know that this hydride can attack this oxygen, kick up electrons. Now this oxygen's got a negative charge, and we've got two hydrogens on it, and then this alkoxide's still just hanging out. You really can't stop at the aldehyde using lithium aluminum hydride. It's a lot more reactive than the starting material, so it's going to be instantly consumed by any lithium aluminum hydride that's around. All right, and then in the next step, step 2, we've got water around. And water is really just used to quench this reaction. Oh. So we can protonate this alkoxide, and then this alkoxide can also get protonated. So I'm kind of streamlining this in one step. Oh. And we've got our alcohol plus our alcohol. So just like we saw, we were able to basically deconstruct an ester into two different pieces. Does that make sense? Lithium aluminum hydride is a really, really strong reagent. Why do you think, if we look at it, we have to split it into 2 steps versus 1 step with sodium borohydride? Does anybody have an idea? It's a small thing, but it's a really important thing. What else can hydride do? Acid-base chemistry, right? We use sodium hydride as a really strong base. Lithium aluminum hydride is a really strong source of hydride. So if you were to run this in water, all it would do is deprotonate the water. Sodium borohydride is a lot more weak. It's not as readily basic, so it won't deprotonate your alcohol or your water solvent. So you can actually do sodium borohydride in one pot and mix everything together, whereas with lithium aluminum hydride, you have to separate it out to avoid potential acid-base chemistry from occurring. So it's an important distinguishing feature. Does that make sense? All right, let's make a little note too. All right, so let's take a look at our aldehyde versus our ketone versus our ester versus our carboxylic acid. And I'm going to make a little chart here. Oop. And we'll compare which ones work with each reducing agent. So sodium borohydride, which one will it reduce? Yeah, the aldehyde for sure. And let's draw in the product we would get. We know with aldehydes we would get a primary alcohol. Is that the only thing it will work on? Not quite. The carboxylic acid won't be reduced by sodium borohydride. It was only aldehydes and what else? Ketones. So if we reduce a ketone, we can make a secondary alcohol. However, down here we get no reaction and no reaction. Oops, sorry. This should be LiAlH4. Excuse me. All right. And then we said lithium aluminum hydride will work with reducing our ester into two different alcohols. And then with carboxylic acids, we'll actually cover this mechanism a little later. You can also use that to create a primary alcohol from a carboxylic acid. Do you think it will work with aldehydes and ketones? Yeah, definitely. In fact, it's so strong that it will basically react with those super duper quickly. However, most of the time, chemists prefer to use the most gentle reagent possible just because it's easier to work with from a practical standpoint, right? So in this case, lithium aluminum hydride will reduce aldehydes, ketones, esters, and carboxylic acids, but sodium borohydride will only reduce aldehydes and ketones. Make sense? Okay, so let's continue on and we'll discuss diols a little bit and then do some practice as well. So a diol is really just two alcohols coming off of the same molecule. And we already know a handful of ways to make diols, but let's quickly review them just for fun. We have two ways of making syndiols, which in this case would give us a meso compound. And then we've got one way of making an antidiol, which would give us a set of enantiomers. So I'll write plus En. We said we could use KMNO4 and then what else? NaOH. Yeah, and we have to run this cold. If you heat it up, you'll actually form two carboxylic acids, so you have to be very careful about temperature. What was the other way? Yeah, OSO4, followed by NaHSO3, and water. And then what about with antidiols?
MCPBA.
Yeah, exactly. MCPBA. Metachloroperoxybenzoic acid.
Not the first two.
And then second step, we treat this with water. So diols are really important. However, they've got some goofy naming rules. So I wanted to briefly go over the naming of diols. So let's take a really, really simple diol. This has a couple different names. One thing you could do is identify the parent chain, and you'd say, hey, this is 2 carbons long, so it's got to be some sort of ethane derivative. So you could call this 1,2-ethane diol. However, if you said that, people would look at you a little funny and they'd say, what are you talking about? The more traditional name for a lot of these diols, like this one, would be ethylene glycol. Have you guys ever heard of ethylene glycol or propylene glycol? Yeah, it's oftentimes used as antifreeze too, so you might...
Should there be an L in there for glycol?
It's ethylene glycol. Sorry. Ethylene glycol. Okay, and this confused me for a while, but This basically is just code for a diol. And I always wondered, why do they call it ethylene? Because you see that ENE suffix. To me, that would imply a double bond, right? And that gets into these weird IUPAC naming rules. And I'll show you guys what's going on here. If you've got a CH2 group in between two other groups, this is referred to as a methylene linker. And if you've got something where it's CH2, CH2, this is an ethylene. It doesn't mean that there's any sort of pi bond or alkene in there. It just means that it's an ethyl group in between two other things. Does that make sense? Oftentimes you might have heard of propylene glycol. That's similar, where you just have 3 carbons in a row in between 2 alcohols.
Does the ACS exam use the common or the...
That's a good question. With the ACS exam, I believe they use the more common names. So you might see something like ethylene or propylene glycol. However, they normally will draw it out for you as well. Okay, so let's take a look at preparing diols. We know we can prepare them using addition chemistry, but we can actually do it with reduction as well. All right, so let's do a little bit of practice here. Let's do this compound, and I'm going to treat it with sodium borohydride and an alcohol, and I want you guys to help me figure out what the product would be for this reaction. Then I'll give you guys a second one to work on. So sodium borohydride, which functional groups can that reduce? Aldehydes and ketones, right? Then give me a thumbs up if you think you got both the answers. Yep, it's an ethoxy group, so O-ethyl. All right, give me a thumbs up if you think you got it. A few people? All right, let's go through the first one. The first one's fairly easy. So we've got a ketone and aldehyde. We know we can reduce both of those. So we'd have an alcohol from that ketone, specifically a secondary alcohol. And then over here, we would have a primary alcohol from where that aldehyde used to be. All right, for fun, let's name it.
What about the enantiomer? Would there need to be stereochemistry?
Okay, that's a good question. So the question was, would there be stereochemistry?
Yeah.
Do you think sodium borohydride is going to be specific with which side of that ketone it's attacking?
No.
Probably not. So in this case, you'd end up with a racemic mixture of enantiomers. So if you really want to be picky, you could write this plus En. However, if you don't specify stereochemistry, meaning you don't have a dash or a wedge, you have a straight line, it's assumed to be racemic in your textbook. Okay, so let's go ahead and name this. So we know longest parent chain is 1, 2, 3, 4, 5, 6. So if we were to name this, it'd be 1, 5, what?
Say hexane diol.
Yeah, 1,5-hexane diol. Typically, once you get above propylene, you don't use that glycol anymore. You'd use the traditional diol nomenclature.
Butylene glycol.
Yep.
So I thought they were just talking about the carbons between the two. So wouldn't that just be 5? And then there's a 6th one hanging out the end?
Yeah, with diols, you want to identify the longest carbon chain where you have alcohols coming off of that parent backbone. So you see how the parent backbone, we've got a hydroxy group coming off of position 1 and 5. The longest continuous chain that has both of those groups is 5 or 6 carbons long.
So we're not doing like the ethylene glycol kind of like where there's that E?
Yeah, with more complicated ones, you go with the diol route, not the glycol route. But I wanted to show you the glycol naming because it's very, very common. It's just been around forever. Okay, so let's do the next one. The next one, we know we can reduce this ketone. We can reduce this ketone. What about the ester? No, untouched. So we'll just write unreactive. Okay, that means our final product will have an alcohol and an alcohol. And then the ester would just kind of hang out on its own. It wouldn't do anything. So we'll discuss naming of esters when we get to that chapter, but for right now, don't worry about naming more complicated compounds that contain diols.
There'd be multiple enantiomers there.
Yes, in this one, how many enantiomers do you think we would have? Or how many stereoisomers, I should say? 4, right? Because we've got 2 stereocenters. So in this case, we would get a pretty awful mixture out. All right, now my favorite part. We get to talk about fun reactions. This guy. This guy is named Victor Grignard. And the reaction we're going to cover next is named after him, but you can make alcohols using his reagent. There's a couple important facts you need to know about him. He won the Nobel Prize in 1912. And he was covered under the organometallic transformation that was occurring in the early 1900s. The second thing you guys should know is that he's one of my favorite chemists because he has the best mustache ever. Whoop. I don't think there are any other chemists that have a mustache quite as elegant as his. We were joking in grad school that he probably didn't need to wear safety goggles because if something exploded, it would just be caught by his mustache. So the Grignard reagent was named after him. And essentially it's an organomagnesium reagent. And it's still very, very commonly used despite being over 100 years old. And in order to make a Grignard reagent, you need an organohalide. So X in this case could be bromine, chlorine, or iodine. You typically don't see it with fluorine at all. Fluorine's a really, it forms a really strong bond with carbon. And then all you need to do is get magnesium, grind it up or get fresh magnesium turnings, and then mix it together. And you have to run this in an aprotic solvent, and we'll talk about that in a second. And typically the aprotic solvent you use is some sort of ether. So diethyl ether or THF are very common, but it has to be an aprotic solvent. When you do this, the magnesium will actually insert itself in between the carbon-halogen bond. Another way of thinking about this molecule is as an ion pair. Why is it fair to call this an ion pair? Yeah, the electronegativity difference is huge between carbon and magnesium, right? In Gen Chem, you guys were taught that anytime you've got something on the right-hand side of the periodic table with something on the left-hand side, that it's ionic, right? So in this case, this has a lot of ionic character to it. So you can draw it either way in my book. I'm fine with it. However, in your textbook, they normally show it as this top form. If it helps you, though, you can draw it out as this bottom form.
Shouldn't it be magnesium 2 plus X minus?
No, magnesium as an ion is 2 plus, but the halogen is negative. So 2 plus with a negative 1 has a net charge of positive.
Oh, so you're not showing formal charges. Okay.
Yeah.
I was in-
So if we look at this reagent, this is super powerful because we've created a carbon with a negative charge. That means it's a good nucleophile. The other problem, though, is that it's a super strong base. So if we go back and we think about our solvent choice, if we were to use water, what would be a problem? Yeah, it would just deprotonate your solvent. So in this case, you have to choose a solvent that has a super high pKa value. And ethers, in this case, will actually stabilize this ion pair because those lone pairs will essentially wrap up that magnesium cation. So ether is far and away the best solvent you can use for these Grignard reactions. So let's take a look at a common reaction with Grignard reagents. So let's say I've got acetone, and I'm going to first treat this with ethyl magnesium bromide. And then afterwards we'll treat it with water. But what I want you guys to do is to try to figure out what you think the intermediate would be if we treated this ketone with ethyl magnesium bromide. So I'll give you guys a minute to work on this, but check with your neighbor and see if you agree with the reaction. I'll give you guys a hint too. We said that this is going to be a super strong nucleophile. Where's the electrophile then? Yeah, the carbon right here is going to be electrophilic. And why is that electrophilic?
Because it's just a strain because of that oxygen.
Yeah, exactly. This oxygen's pulling all that electron density away from that carbon, which makes that carbon really electrophilic. And we know that this carbon right here is going to be our nucleophile. So using our intuitive reasoning, we could say our nucleophile is going to attack our electrophile, and then what? Yeah, kick up electrons onto that oxygen. We can't have a Texas carbon. So we'll kick up electrons over here. And then in this case, we've got magnesium bromide as our countercation. So can you guys see how essentially we had this ethyl group here, right? So these two carbons are now located right here and here. So we've added on a new ethyl group. Oftentimes students get confused with these Grignard reactions, so I would recommend that you number your carbons. That way you don't accidentally add too many or not enough. Sometimes it's easy to get those mixed up. All right, and then in step 2, all we need to do is quench this with some sort of weak acid, so we could use water even. When we do this, we've created an alcohol, and in this case we've created a tertiary alcohol. With lithium aluminum hydride and sodium borohydride, I told you guys there was no way you can make a tertiary alcohol. Now we've got a nice way of making a tertiary alcohol. So this is a good workaround if you do need to make some sort of tertiary alcohol. Okay, so let's try a couple more. And I want you guys to check your answers with your neighbor. So we've got cyclohexanone with ethyl magnesium bromide. I'm going to abbreviate it. And then we're going to quench it with water. Let's get our product there. And then for our second example, I'll do it down here. We're going to change things up a little bit. We're going to do methyl magnesium bromide in excess, and then we're going to treat this with water.
No, it's supposed to be methyl, not ethyl.
Yep, for the second one it's methyl, not ethyl. And with the second one, it may help if you draw the full mechanism too, and we'll do it as a class together. But I want to see if you guys can figure it out. It's pretty similar to a reaction we've already seen. All right, give me a thumbs up if you got the first one. All right, let's do the first one as a class, and then we'll go through the second one a little bit more slowly, because the second one's more complicated. All right, so with these sorts of reactions, you could say, you know, this ethyl group essentially has a negative charge. This magnesium's got a positive charge. We know this carbon's nucleophilic. It's going to attack our ketone, kick up electrons. So now we've got a negative charge here. We've added on an ethyl group, and then we said in step 2, where we add water, we're essentially just going to protonate this, right? So pretty straightforward way of adding carbons. Let's do the same thing with the second one, though. And in this one, I'm going to actually separate this out a bit more. So we know that this methyl group's got a negative charge. The magnesium's positive. And we know that the negative charge wants to attack the electrophile. So we're going to attack in, kick up electrons. now this oxygen's got a negative charge. I'm just going to write CH3 here. That's where our methyl group was added. What do you guys think will happen next? Are we just going to protonate it? Yeah, exactly. We saw previously that this can act as a leaving group, right? So in this case, this oxygen can clamp down, kick off this methoxy group.
Acid-base chemistry is the most quick reaction.
Yeah, that is a good point. Acid-base chemistry is super duper quick. However, in this case, it's so unstable, it's going to quickly fall apart.
Is it because of the strain created by having two oxygens and one of them having a negative charge?
Well, let me rephrase it another way. We haven't even introduced an acid yet, so there's really nothing left to protonate it.
Oh, I guess we already went one.
Yeah.
Okay.
Okay, so now we've got that excess methyl magnesium bromide. Where magnesium's got a positive charge, the methyl's negative. We've got a ketone floating around. So we can do this one more time. So now we've got two methyl groups added into that electrophilic carbon. And then we've also got this methoxy group that's just hanging out. So we have added in 2 equivalents of methyl magnesium bromide. Can we add in a third? What do you guys think? No, because we don't have any leaving groups to kick off. We'd be forming Texas carbons and violating a lot of rules. So at this point, we're essentially exhausted. And at this step, we can add in water. And water, we know, will protonate both of these. So we would end up with our alcohol plus our methanol. Oops. What would the name of the larger alcohol be?
No.
2-pentanol.
So let's go ahead and number this.
No.
1,
Two.
2
Two
methyl.
pentanol. Two methyl.
So let's name this. We know it's a pentane parent. So it would be 2-methyl 2-pentanol. Do we have to worry about stereochemistry here?
No.
No, we don't have any stereocenters. So, like I said, this is a really nice way of making tertiary alcohols, and you can even use this to react twice with esters because you've got a leaving group built in. All right, let's do a couple more. Let's do it in a little bit different order. And let's try to figure out what product we would get out after all of these. So I'll make this worth 4 points.
Well, it's going to make this. Well, it's going to make this magnesium bromide. Magnesium is rich in stuff in the bond right here. So, watch, then it's going to do this.
I'm not worried about the fact that we're slowing down the shower. You know, half less than a million reactions. I know, right? I got so used to getting slammed with reactions.
So what happens after we add in the magnesium?
It inserts itself.
It inserts itself? Okay. So let's break this down into steps. All right, we know if we do this, now we've got MgBr, where essentially that magnesium's got the positive charge and the carbon's now negative. Okay, and then we're going to react this with our ketone. So what's going to happen here? Yeah, nucleophilic attack, right? This carbon on the benzene is super negative, so it's going to attack our ketone, kick up electron density. Now this oxygen's got a negative charge. We've got our two methyl groups. And then last but not least, we've got our water floating around. So this alcohol can grab this proton, and that will give us our final product. This is a really, really valuable tool for adding on carbon atoms to your molecule. The only other way we know of is by alkylating alkynes, but this opens up a whole new realm of reactivity for us.
Isn't it still just a substitution reaction to add a carbon?
It's still just nucleophilic attack. It's not like an SN2 substitution, but it is a nucleophilic attack. All right, let's do one more, and then we'll call it quits for the day. All right, let's say I've got this guy, and I react it with methyl magnesium bromide, followed by water. Or actually, let's just do H3O plus. We'll do a weak acid. What product will we get out? We'll make this worth 4 points. Is anybody going to call me out on this? Does anybody see something that's wrong, or that looks funny, or that might cause problems? Acid-base chemistry, yes, exactly. So we said this is a strong base. Carboxylic acids, by definition, are acidic. So really, all you're going to do in step 1 is deprotonate your carboxylic acid. And then in step 2, what are we going to do? Reprotonate our carboxylic acid. So this was a trick question. If we do this, we're not going anywhere. So really, Grignard reagents are only useful with aldehydes, ketones, and esters. They don't work with carboxylic acid. So that's something to be aware of when you're doing these Grignard reactions in your textbook. All right, I think we'll leave it off there. And then tomorrow, when we come in, we'll do a little bit of synthesis using our Grignard reactions, and then we'll continue on a little bit.
Silly, silly.